Section: Introduction. We've observed a significant growth in the creation of expert models that are fine-tuned for specific tasks or domains, thanks to the availability of high-performing pre-trained language models. These expert models often use a method called parameter-efficient fine-tuning, PEFT, which involves adding small, specialized modules that only tweak a few parameters. These modules, like low-rank adapters or EA-cubed vectors, are compact enough to be easily shared, leading to a vast distribution of these adapters across various platforms. For instance, there are over 17,000 adapters available on the Hugging Face Model Hub. On the other hand, extremely large-scale language models, LLMs, are being used as versatile AI systems capable of handling any task without needing specific training for each one. This is possible because LLMs can generalize to new tasks they weren't directly trained on, a capability that's often enhanced through multitask fine-tuning. This approach contrasts sharply with the method of creating specialized models for each task. Given the widespread use of specialized PEFT modules and the general-purpose nature of LLMs, we're prompted to ask if we can use a large collection of these specialized modules to improve an LLM's ability to generalize to new tasks without prior training. This idea is appealing for several reasons. It could lead to the decentralized development of versatile language models, which would otherwise require significant centralized computing resources. It also offers a way to make use of the extensive effort and resources already invested in creating specialized models. This strategy could work well, considering that multitask training has been shown to enhance generalization to new tasks, and combining specialized models could be seen as a form of multitask learning that doesn't need simultaneous access to data. Previous attempts to solve this problem have involved learning a strategy to choose the best expert model for a given input after the fact. However, these methods often fall short of an ideal solution that always picks the best expert. To find a better solution, we note that PEFT methods usually add small trainable modules throughout the model, and some models make routing decisions for each token separately. In our work, we explore improving zero-shot generalization by dynamically choosing which expert modules to use for each token and at each stage of processing. This approach could allow the model to better adapt to new tasks by leveraging the strengths of different experts. Building on this idea, we introduce a new method called post-hoc adaptive token-wise gating over an ocean of specialized experts, PHATGOOSE. This method enhances zero-shot generalization by using PEFT modules in a novel way. After training a model with PEFT, we freeze it and add a trainable gate for each module. This gate decides whether or not to use the module for each token in the input. Training these gates requires minimal additional computing resources. During inference, we use a standard top-K strategy to decide how to route tokens to different modules. We tested PHATGOOSE with T5 family models and found that it not only performs better than previous methods of combining experts or choosing a single expert but also, in some cases, outperforms direct multitask training. Our analysis shows that PHATGOOSE can use a wide range of modules to tackle a task, often achieving better results than the best single expert model. Overall, our work lays the foundation for a new approach to developing versatile AI systems in a decentralized manner. Section Summary. The section discusses the proliferation of specialized models created through parameter-efficient fine-tuning, PEFT, techniques and the potential of leveraging a large collection of specialized modules to improve zero-shot generalization of a base language model. The authors introduce a method called lmttPHATGOOSE, which recycles PEFT modules by introducing a per-module gate to determine how to route different tokens to different modules during inference, and demonstrate its effectiveness in improving zero-shot generalization on standard benchmarks, outperforming prior methods and explicit multitask training in some cases. This work lays the groundwork for a promising new framework for the decentralized development of generalist AI systems by combining abilities from multiple specialized models to produce better performance. Section: Decentralized development of zero-shot models. We're working on a way to let people work together to make models better at handling tasks they've never seen before, without having to share their data. We do this by having each person improve the model for their own specific task using a method called PEFT, which is easier and cheaper than other methods. They add little updates, called modules, throughout the model. We don't want to make this hard for them, so they only need to share these modules, not their data. We're trying to make the model better at tasks it hasn't been trained on, not just the ones it has. This is tricky because we need to figure out how to combine the expertise from different people's modules to tackle new tasks without using a lot of extra computing power. Also, the model has to decide how to use these modules based on just one example of the task, without having a dataset for it. Some methods pick one expert model based on the task, but we're trying something different. We're developing a method called post hoc adaptive tokenwise gating over an ocean of specialized experts, or PHATGOOSE for short. This method uses the modules people have made and decides which ones to use for each part of a task to get the best results on tasks the model hasn't seen before. Here's how it works. Let's say someone uses a popular method called LoRa to make their module, which tweaks the output of certain parts of the model. After they're done, they add a special gate that decides whether or not to use their module for a specific part of the input. They train this gate with the same data they used before, but they don't change anything else in the model. Once everyone shares their modules and gates, PHATGOOSE uses these gates to decide which modules to use for each part of a new task. It scores the modules based on how well they match the task and picks the top ones. Then, it combines their outputs in a smart way to get the final result. We think this gate approach is good because it lets the model use the right modules for the right tasks, based on what each module is good at. We tested this idea and found it works better than just averaging everything or training everything together from the start. So, PHATGOOSE lets us use everyone's modules to make the model better at new tasks without needing their data again and without a lot of extra work. We just need to train the gates a little, which isn't too hard. Section Summary. In this section, the authors aim to facilitate the collective improvement of zero-shot generalization capabilities of a model by allowing individual contributors to share specialized PEFT modules without requiring access to each other's datasets. They propose a method called lmttPHATGOOSE, which involves contributors training task-specific gate vectors and using them for top K routing during inference, enabling the model to route based on the relevance of the PEFT modules for a given input activation. This approach allows for the recycling of PEFT modules without needing access to the training datasets and without incurring significant additional costs, ultimately leading to improved zero-shot performance. Section. Experiments. We've developed a new method called lmttPHATGOOSE and now we're going to test it out. Our main goal is to see how well it can help T5 models perform on tasks they haven't seen before, a concept known as zero-shot generalization. We're going to do this by using two different groups of specialized models, called expert pools, and checking how well our method works on 3 different tests. First, let's talk about our setup. Previous research has shown that training T5 models on a bunch of different tasks at once can make them really good at handling new tasks they've never seen before. This approach is pretty popular for testing out new ideas, so we decided to use it too. Specifically, we're using a beefed-up version of the T5 model that's been trained a bit more on a huge dataset called C4. For our expert pools, we're looking at 2 different collections of datasets. One is a set of 36 tasks that were used to train another model called T0. The other is a much bigger collection called FLAN, which has all sorts of tasks designed to test different abilities of models, but we're only interested in the ones that are set up for zero-shot learning. This gives us a total of 166 models from the FLAN collection. We're using something called low-rank adapters, or LoRas, for our expert modules, but our method could work with other types of modules too. We trained one of these modules for each task in our collections, ending up with either 36 or 166 expert models depending on the collection. For testing, we're using 3 benchmarks. One is a set of tasks that were not included in the T0 training, and the other 2 are parts of a big collection of tests called Big Bench. Big Bench Hard is really tough for current models, and Big Bench Light is a bit easier but still covers a wide range of abilities. We had to leave out some tests that our model couldn't handle, though. We trained our LoRa's with specific settings, like a certain number of steps and batch sizes, and then we did something similar for the part of our method that decides which expert to use for a given task. Now, let's talk about what we're comparing our method to. There are a few different ways people have tried to improve zero-shot generalization before. One way is by finding the expert model that's most similar to a new task and using that. Another way is by averaging the outputs of all the expert models for a given task. There's also a method where you merge the expert models into one big model. We're testing our method against these to see how well it does. In summary, we're putting our new method, lmttPHATGOOSE, through its paces by seeing how it stacks up against other ways of improving how models handle tasks they haven't seen before. We're using a couple of different sets of expert models and a few different tests to get a good idea of how well it works. Section Summary. The section describes the experiments conducted to validate the lmttPHATGOOSE approach, focusing on improving zero-shot generalization in T5 models. 2 different expert pools and 3 zero-shot benchmarks were considered, with the experiments involving explicit multitask training of T5 on prompted datasets. The experiments also compared lmttPHATGOOSE against various baselines, including retrieval-based routing and average activation, as well as merging of expert modules. Section: Multitask. We explore the concept of multitasking in our study, acknowledging that training models simultaneously with data from various experts isn't feasible in our scenario. However, understanding its importance in enhancing zero-shot generalization, we still consider it as a reference point. Since we don't have the resources to develop our own multitask models, we rely on existing ones for comparison. Specifically, we use the T0 to 3B model for the T0 held in datasets, noting that for the FLAN datasets, a perfectly matching model isn't available. The closest we have is the FLAN T5XL model, but it's trained on a slightly different set of datasets, so direct comparisons should be taken with caution. We also introduce the concept of an oracle routing scheme, which selects the best performing expert for each dataset. This method isn't zero-shot but sets a high-performance benchmark for our study. Similarly, we identify the best single expert across all datasets, which, while not zero-shot, represents the optimal performance one could expect without dynamic routing. In our results, we find that our model, lmttPHATGOOSE, generally outperforms previous methods, especially in the T0 held-out tasks, closely approaching the oracle's performance. Interestingly, lmttPHATGOOSE does well against the multitask T03B model despite being trained without direct access to all data simultaneously. When comparing to other methods, lmttPHATGOOSE shows a slight underperformance in one area but significantly leads in others, particularly when the number of experts increases. We notice a trend where lmttPHATGOOSE performs better on tasks requiring logical reasoning as the number of experts grows, but not as well on tasks that demand specific knowledge. This suggests that tasks benefiting from reasoning skills improve with more diverse expert input, while knowledge-heavy tasks might suffer due to the dilution of specific expertise. Our findings underscore the effectiveness of lmttPHATGOOSE, especially when compared to previous approaches like retrieval and average activation, highlighting the advantages of our model's design. The comparison suggests that the ability to dynamically combine expertise is crucial for zero-shot generalization. To further understand lmttPHATGOOSE's success, we conduct a qualitative analysis, examining how well its routing decisions align with the oracle's and whether this alignment correlates with performance. By calculating the routing distribution for lmttPHATGOOSE and comparing it to the oracle's using KL divergence, we find little correlation between alignment and performance. This indicates that lmttPHATGOOSE often finds effective routing strategies that differ from the oracles. Visual examples of routing decisions show that lmttPHATGOOSE can outperform the oracle by leveraging a diverse set of experts, particularly in scenarios where it diverges from the oracle's choices, showcasing its ability to enhance generalization through effective expert combination. Section Summary. The section discusses the evaluation of a model called lmttPHATGOOSE in comparison to various baselines and routing methods. Despite being trained in a decentralized manner, lmttPHATGOOSE generally outperforms prior methods, especially on T0 held-out tasks, and consistently matches or outperforms the multitask baseline T0 to 3B. The model also outperforms all other routing methods when the expert pool is expanded, highlighting the importance of future work on learning post-hoc routing among specialized experts for zero-shot generalization. Section. Related work. We've been looking into how to efficiently direct questions to the most suitable large language models, LLMs. Some recent studies have developed methods to choose the right generalist LLM for a given query. One approach involves training a binary classifier for each LLM to predict if it will answer a question correctly, helping to pick the best LLM when needed. Another method uses a router to spread out questions among different LLMs based on a ranking system, which helps avoid using all LLMs for every single question. Unlike these studies, we're more interested in how to route questions to specialized models instead. In the realm of learning from a few examples, some researchers have explored reusing specialized components. For instance, LORA Hub optimizes how to blend specialized modules for tasks with just a few examples to learn from. Another approach learns a function to decide which module to use, showing results similar to LORA Hub. Some have focused on creating experts for specific tasks and then finding and combining the most relevant ones for a new task using task similarities. Others have developed task-specific adapters and combined them in a way that outperforms training on multiple tasks at once or fine-tuning the entire model on each task. There's also work on improving how models generalize to tasks they haven't seen before by training on different data clusters or merging models designed for specific aspects like content and style. When it comes to merging expert models, some have tried combining model parameters in a way that the resulting model can handle new datasets. Improvements include matching parts of models to reduce conflicts and solving a set of equations to blend models effectively. However, these methods usually need a set of examples to fine-tune the blending process. One study managed to merge models for summarization in new languages without needing such examples, using unlabeled data and a technique to minimize uncertainty in choosing how to combine model parameters. Multitask learning involves training a model on various tasks simultaneously, which has been shown to help models perform better on new, unseen tasks. This is slightly different from our focus but still relevant. Some have developed models that can decide which expert to use for a given input, training the decision maker and experts together on all tasks. This approach has proven beneficial for handling tasks the model hasn't encountered before. Others have found that organizing expert knowledge into blocks or training a task-specific router can be more efficient and just as effective. These studies, while focusing on different aspects of model training and task handling, offer insights that could be valuable for our work on routing among specialized models. We're excited about the potential to apply what's been learned in these areas to our problem, even though our situation doesn't involve having access to all data at once.